Hello and thank you for visiting my poster with the title Survival, Multimodal and Neural Ordinary Differential Equations, or in short ISMNode, for mortality predictions of patients with severe lung disease. My name is Thomas Linden. I'm a PhD student in computational life sciences and doing research at Fraunhofer in Germany. Coming to the abstract. So my research is focused around developing risk models using clinical routine data. And the motivation of this work arose during the COVID pandemic, where we were facing increasing admissions to intensive care units. So medical decisions taken in intensive care units are often time critical, and therefore timely risk prediction is very important for optimal care. And as you can imagine, in particular for identifying high risk patients as early as possible. But this is very challenging because we have to deal with a number of challenges, which are, for example, we have right-censored, multimodal, multivariate, irregular time series with missingness. I know this sounds quite complicated, but I hope that I can disentangle this a little bit during this short walkthrough. Our proposed method, the SM node, addresses a number of frequent major challenges. For example, it can handle longitudinal and static data. Static data, for example, everything which does not change after ICU admission. Could be age, gender, um, prior chronic diseases. The model can handle irregular multivariate time series, for example, as they appear from sensors from the bedside every second, or blood values from the lab every day. It can handle right sensor data, and it does imputation of missing values, and moreover, it does not make any assumptions about distributions which need to be checked or satisfied. Now let's talk about the model and how it works. In the middle of this poster is a model section in dark gray showing the overall model architecture. Starting from the left, there is this big white box with three sections, colored red, blue, and black. In the red section, the static data goes in and the lower dimensional embedding, shown as red vector, goes out. In the blue section, multivariate time series data with missingness goes in, then missing values are imputed, then embeddings are learned in the time and feature space, and then the blue embedding goes out. The black box is where the neural ODE magic happens. The combined static and time series embedding, here shown as blue-red vector, goes in, and this defines the initial value for the initial value ODE problem. Then the ODE is solved and the model ultimately returns predicted survival probabilities over time. In general, the ODE could be an arbitrary neural net to learn the dynamics. But in our case, we use a given ODE system which describes the time evolution of probabilities. The model was evaluated on the MIMIC3 dataset, a large public available ICU dataset with over 60,000 ICU admissions. From that, we extracted two cohorts. On the one hand, patients suffering from pneumonia with around 4,000 admissions, and on the other hand, mechanically ventilated patients with around 13,000 admissions. The mortality rate is between 12 to 15%. Now I'm in the results section. Here I show that we compared our model against two other widely used methods for time to event modeling: a gradient boosting machine and DeepSurf. DeepSurf is a nonlinear neural net version of the very popular Cox regression. The metric we use is a concordance index, often called C-index, which can be understood as a generalization of the AOC for time to event models. This means a score of 0.5 is as worse as random guessing, and a score of 1 means a perfect model. The upper figure shows the model performance by cohort, where the left panel are the pneumonia patients and the right panel are the mechanically ventilated patients. The different models are indicated by the colors. The higher the bar, the better the model. Our model, shown as green bar, performs competitive. The lower figure shows the performance over time for days 2 to 7 after ICU admission. As a quick note, days 1 and 2 are used for training the models. Again, pneumonia is left and mechanically ventilated is right. The higher the line, the better the model at that time. We can see that our model performs competitive. Precision medicine is strongly dependent on machine learning. Intensive care data constitute an important source of such clinical routine data. They principally exist in large quantities and allow for obtaining insights into the longitudinal medical history of individual patients under real-world conditions, but they have not been collected for research purposes. Our model shows state-of-the-art performance and provides an efficient interpretation of missing values. Moreover, as a neural net, it inherently supports fine-tuning, which is convenient for transfer learning. As it is built upon the multi-neural ODEs, our model is extendable to a generative training, which in principle supports two aspects. One is generative pre-training, and another one is patient simulation. In this presentation, we consider only two so-called states, alive and death, but the model is in principle extendable to more than two states. The main downsides of our approach are that the hyperparameter tuning and estimation of feature importance for model explanations are computational very demanding. Thank you for taking the time to visit my poster. I'm really looking forward to your questions. If you like, please write me an email.